This is the EdExcel A-Level Further Maths Paper 2 from the 2023 series, and this paper covers the Core Pure Maths 2 section. Question number 1. Figure 1 shows a sketch of the curve with polar equation r equals 2 multiplied by the square root of hyperbolic sine theta plus hyperbolic cosine theta, where theta is in between 0 and pi. The region R, shown shaded in figure 1, is bounded by the initial line, the curve, and the line with equation theta equals pi. We have to use algebraic integration to determine the exact area of R, giving an answer in the form Pe to the power of q subtract r, where p, q and r are real numbers to be found. We can find the area of a sector when we have polar coordinates using the formula a equals 1/2 multiplied by the integral of r squared with respect to theta. And so therefore, knowing that r is equal to 2 multiplied by the square root of hyperbolic sine theta plus hyperbolic cosine theta, the area will be given by 1/2 multiplied by the integral of 2 multiplied by the square root of hyperbolic sine theta plus hyperbolic cosine theta squared with respect to theta in between 0 and pi. So we are required to work out this integral. So what we have here is 1/2 times by 2 squared, which is 2. So we have 2 multiplied by the integral of hyperbolic sine theta plus hyperbolic cosine theta with respect to theta in between 0 and pi. And notice, when we square the square root disappears. So we've got 2 multiplied by. Now if I work out the integral of hyperbolic sine theta, we end up with hyperbolic cosine theta. And if we integrate hyperbolic cosine theta, we end up with hyperbolic sine theta. So we are evaluating 2 multiplied by hyperbolic cosine theta plus hyperbolic sine theta in between 0 and pi. So we have 2 multiplied by, well, hyperbolic cosine theta is the same as 1/2 multiplied by e to the theta plus e to the negative theta, and hyperbolic sine theta, that's the same as 1/2 multiplied by e to the theta subtract e to the negative theta. And of course, we integrate between 0 and pi. And if we simplify all this, we end up with 2 multiplied by e to the theta, and we need to evaluate this between 0 and pi. Well, what we will end up with once we substitute these limits in is 2e to the pi subtract 2. And so therefore, we can see then p is equal to 2, q is equal to pi, and r is equal to 2. Question number 2. Part A. Write down the Maclaurin series of e to the x in ascending powers of x up to and including the term in x cubed. In the formula book, we have e to the x given by 1 plus x squared over 2 factorial plus other terms plus in general x to the r over r factorial, and then we continue this for higher order terms, and this is for all values of x. Which means then, for part A, e to the x is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus higher order terms. Part B, hence without differentiating, determine the Maclaurin series of e to the x subtract 1 in ascending powers of x up to and including the term in x cubed, giving each coefficient in simplest form. Well, instead of us having an x in our power, what we have instead is an e to the x subtract 1 as our power. So what we can do is think about this e to the x subtract 1. Let's deal with that first. So for part B, if we consider the e to the x subtract 1, well, e to the x using the result we found in part A, that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And then we subtract 1. And so therefore you can see e to the x subtract 1 is given by x plus x squared over 2 plus x cubed over 6. You'll find the 1 subtract 1 gives 0, 2 factorial is 2, 3 factorial is 6. So what we are required to do is use our result which we found in part A, but instead of using an x, we'll replace the x with the e to the x subtract 1. So we have e to the x subtract 1. Our first term is given by 1. For our next term, instead of us having an x, we have the x plus x squared over 2 plus x cubed over 6. And then we add on to this x plus x squared over 2 plus x cubed over 6 squared, and then we divide by 2 factorial. And then we add on to this x plus x squared over 2 plus x cubed over 6 cubed divided by 3 factorial. And then we've got the higher order terms. Now, if we attempt to simplify all this, well, we've got this one, and then we have this x plus x squared over 2 plus x cubed over 6. But then, for this term here, what I'm going to do is rewrite this as x plus x squared over 2 plus x cubed over 6 multiplied by itself. And then this is divided by 2 factorial, which is 2. And then we add on to this x plus x squared over 2 plus x cubed over 6 cubed over 6. And then we've got the higher order terms. So now let's try to simplify this as much as possible. Well, we've got this 1, and then we've got this x plus x squared over 2 plus x cubed over 6. But now, what I need to do is multiply these two brackets up to and including the terms involving x cubed. So, we have x times by x, which is x squared. Then we have x times by x squared over 2, which is x cubed over 2. Then we have x squared over 2 multiplied by x, which is x cubed over 2. And then anything else beyond that is a higher order term. And then I need to divide this by the 2. And then I have the x plus x squared over 2 plus x cubed over 6 cubed. And then I've got the higher order terms. So now let's try to simplify all this. Well, if we try to simplify all this, I've got 1, and then here I've got the x plus x squared over 2 plus x cubed over 6, and then here I've got x squared plus a half x cubed plus another half x cubed. That simplifies to give x squared plus x cubed, and don't forget I'm dividing by 2. And then here, just thinking about what gives me a cube term, I've got the x cubed and I'm dividing that by 6. So I've got x cubed over 6 plus higher order terms. So if we try to simplify all this, I've got the 1, and the terms involving x only, I've just got that x. Then the terms involving x squared, I've got x squared over 2 plus another x squared over 2, so that's x squared. And then thinking about the x cubes, I've got x cubed over 6 plus x cubed over 2 plus x cubed over 6, which gives 5x cubed over 6. And then we've got the higher order terms. So this is the required result in simplest form. Question number 3. We are given this matrix M, negative 2, 5, 6k, where k is a constant, given that m squared plus 11m equals ai, where a is a constant and I is the 2 by 2 identity matrix. We have to determine the value of a and show that k equals negative 9 for part A. So, for part A, we have m squared plus 11m, and using the matrix M, we have negative 2, 5, 6k squared plus 11 multiplied by negative 2, 5, 6k. Let's work this out. Well, we have negative 2, 5, 6k squared shown here, and then we add on 11 times by negative 2, 5, 6k, which is negative 2, 55, 66, 11k. Now let's work this out. We have negative 2 times negative 2 plus 5 times by 6, which is 34. Then we have negative 2 times by 5 plus 5 times by k, which is negative 10 plus 5k. Then we have 6 multiplied by negative 2 plus k multiplied by 6, which is negative 12 plus 6k. Then we have 6 multiplied by 5 plus k multiplied by k, which is 30 plus k squared. And then we add on to this negative 22, 55, 66, 11k. And if we combine these 2 by 2 matrices, well, 34 subtract 22, that's 12. Negative 10 plus 5k plus 55, that's 5k plus 45. Then we have negative 12 plus 6k plus 66, which is 54 plus 6k. Then we have 30 plus k squared plus the 11k, which is k squared plus 11k plus 30. So if we go back to our equation, that's what the left hand side is equal to. And we need to set this equal to a multiplied by the identity matrix. So we have m squared plus 11m shown here, and this is equal to a times the identity matrix a0, 0a. And what we can now do is determine the value of a and determine the value of k. So if we work out the value of a, you can straight away see 12 is equal to a is 12. And to find the value of k, well, we have the 5k plus the 45 equals 0, and if I solve for k is equal to negative 9. Part B, determine the equations of the invariant lines of the transformation represented by M. So, part B, we have this matrix M, negative 2, 5, 6, negative 9, and I'm going to multiply this by some point xy, and because we have an invariant line represented by this matrix, we set this equal to capital X, capital Y. So therefore, we've got this matrix, negative 2, 5, 6, negative 9, and we multiply this by xy. Now we've got this x, and y is the same as mx plus c. And this is equal to, well, here we've got this capital X, and then this capital Y we can rewrite as m times capital X plus c. And this is because we are working out the invariant lines. So let's work all of this out. Well, we've got this capital X, and this is going to equal, well here, I've got the negative 2 times by x, which is negative 2x, and then I've got 5 multiplied by mx plus c, which is 5mx plus 5c. And then I've got this m times capital X plus c, and that's going to equal 6 times by x, which is 6x, and then I've got negative 9 times by mx plus c, which is negative 9mx, subtract 9c. And now that I know what capital X is, that's negative 2x plus 5mx plus 5c, I can replace this capital X with that. So I've got m multiplied by negative 2x plus 5mx plus 5c, and that's equal to what we have on the right side here, 6x subtract negative 9mx subtract 9c. And if I expand the brackets on the left hand side, we've got negative 2mx plus 5m squared x plus 5mc plus c equals 6x subtract 9mx subtract 9c. So for our invariant lines, if we compare everything involving an x, we've got the 5m squared subtract 2m equals 6 subtract 9m. And if I simplify this, we end up with 5m squared plus 7m subtract 6 equals 0. And solving this, you find m to equal negative 2 and 3/5. And if I compare the numbers, we've got the 5mc plus c equals negative 9c. Now, if we think about this m equals negative 2 and substitute back into here, we've got 5 times by m, which is negative 2, times by c, plus this extra c, which is negative 9c. And so what you can see here then is c can take any value. And if we think about the m equals 3/5, I've got the 5 times by m, which is 3/5, times by c, plus c equals negative 9c. And therefore, what you can see here is c is equal to 0 only. So for our invariant lines, we have y equals 3/5 x plus 0c, which is just y equals 3x over 5. And what we also have is y equals negative 2x plus c. These are our invariant lines. Part C, state which, if any, of the lines identified in Part B consist of fixed points, giving a reason for your answer. So for Part C, we see that the y equals 3x over 5 is the line of invariant fixed points, because we don't have a family of solutions here. So we've got this matrix negative 2, 5, 6, negative 9, and that's equal to x multiplied by y, which is 3x over 5, and that's equal to x 3x over 5. So each point is fixed under this transformation, as we see by this equation here. Question number 4, part A. We have to sketch the polar curve C with equation r equals 3 plus root 5 cos theta, where theta is in between 0 and 2 pi. We can use our calculator to help perform this calculation. If we go to the graph sub-menu, let's change the type to a polar. And if we type in our polar curve, we have 3 plus the square root of 5 multiplied by cos theta. And if we graph this, we have something looking like this. Let's auto-fit this. Here is our required polar curve. It looks something like this. We've got our initial line. We've got this line pi over 2, and it crosses the initial line at the point 3 plus root 5, 0. The tangent to C at the point A, where theta is in between 0 and pi over 2, is parallel to the initial line. We have to use calculus to show that at A, cos theta is equal to 1 over root 5. Well, the tangent to C at the point A, that's shown here, and this tangent is parallel to the initial line. So, for part B, y is given by r sine theta, but we know what r is. That's 3 plus root 5 cos theta, and I multiply that by sine theta. Now, because we are interested in this point A, and at the point A, we've got a tangent to our curve C, what we would have to do then is differentiate this result. We need to find dy over d theta because we are parallel to the initial line, and if I use the product rule, we've got v, which is 3 plus root 5 times cos theta, multiplied by u dash, which is cos theta, plus u, which is sine theta, multiplied by v dash, which is negative 5 square rooted, multiplied by sine theta. And if we simplify all this, what we end up with is 3 times by cos theta plus root 5 times by cos theta times by cos theta, which is root 5 cos squared theta, and then we have negative root 5 multiplied by sine theta multiplied by sine theta, which is negative root 5 sine squared theta. So at this point, as we have a tangent which is parallel to the initial line, dy over d theta is equal to 0. And if that's the case, we set this result equal to 0. And what we are required to do is find out what cos theta is. So, I've got the 3 cos theta, I add onto this root 5 cos squared theta, and then I subtract root 5, and then here I multiply by sine squared theta, and if I want my entire equation to be in terms of causes only, sine squared theta is the same as 1 subtract cos squared theta, and that's equal to 0. And this would simplify to 2 root 5 cos squared theta plus 3 cos theta subtract root 5 equals 0. And if I factorize this, I've got 2 times cos theta plus root 5 multiplied by root 5 cos theta subtract 1 equals 0. Now I need to solve this. Well, I would have 2 cos theta plus root 5 equals 0, in which case cos theta is equal to negative 5 square rooted over 2. But because negative 5 square rooted over 2 is not in between negative 1 and 1, cos theta does not equal negative 5 square rooted over 2. And if I solve root 5 cos theta subtract 1 equals 0, I end up with cos theta equals 1 over root 5, which means cos theta is equal to 1 over root 5 only. Part C, hence determine the value of r at the point A. Well, I know for part C that r is equal to 3 plus root 5 cos theta. And I know what cos theta is, that's 1 over root 5. So I've got r equals 3 plus root 5 times by 1 over root 5, which means r is equal to 4 at the point A. Question number 5. The points representing the complex numbers z1 equals 35 subtract 25i and z2 equals negative 29 plus 39i are opposite vertices of a regular hexagon H in the complex plane. The center of H represents the complex number alpha, For part A, we have to show that alpha is equal to 3 plus 7i. For part A, here is a diagram representing the information we've been given. We've got a regular hexagon, and we've got the point Z1 and the point Z2, which are opposite to each other, and their midpoint is what we need to find. So, alpha, that's given by 35 plus negative 29 over 2 plus negative 25 plus 39 over 2i, which means alpha is equal to 3 plus 7i. And if we represent that on the diagram, we see here alpha, the midpoint of Z1 and Z2, is 3 plus 7i. Part B, given that beta is equal to 1 plus I over 64, we have to show that beta multiplied by Z1 subtract alpha is equal to 1. So, for part B, we've got beta equals 1 plus I over 64. And with this, if we work out beta multiplied by Z1 subtract alpha, we've got beta 1 plus I over 64 multiplied by Z1, which is 35 subtract 25i, subtract alpha, which is 3 plus 7i. So if we work out what this is equal to, what we end up with is 1, and that's exactly what we wanted to show. The vertices of H are given by the roots of the equation beta multiplied by z minus alpha all to the 6 equals 1. For part C, for the first part, we have to write down the roots of the equation w to the 6 equals 1 in the form re to the I theta. So for part C, we've got our given equation b multiplied by z minus alpha to the 6 equals 1. And for the first part, we need to solve the equation w to the 6 equals 1. Now this 1 we can rewrite as e to the 2 pi I over k, and if I take the 6th root, we end up with w equals 2 pi I k over 6, which simplifies to e to the pi I k over 3. So w equals e to the pi I k over 3, and what we need to do is substitute in values of k from 0 to 5 to find out our roots. And the reason I substitute in from 0 to 5 is because we've got 6 roots. Now, on our calculator, if we go to the setup menu and then scroll down to where we have the complex mode, we'll change the complex mode to r theta. So now, if I find out what my roots are, well, I've got my modulus of 1, and then my angle is given by pi over 3 multiplied by 0. So my first root is 1. The next one, I've got 1 as my modulus, and then my argument will be given by pi over 3 multiplied by 1. So I have e to the pi I over 3. Next, I've got 1 for my modulus. My argument will be pi over 3 multiplied by 2. So I get w equals 2 pi I over 3. Next, I've got 1. Then I have my argument being pi over 3 multiplied by 3. So it turns out I have w equals pi I. Next, I've got 1. Then I've got my argument being pi over 3 multiplied by 4. So my next root is w equals e to the negative 2 pi I over 3. And finally, I've got 1. And then here I have pi over 3 multiplied by 5, which is w equals negative pi I over 3. Now what I'm going to do is rewrite them in the form a plus bi, just in case I need it later. So if I go to the setup menu, let's change the complex mode to real. So now if I work all these out again, our calculator displays for us all those in the form a plus bi. So for the first one, I've got the 1. For the next one, I've got 1/2 plus root 3 over 2i. Next one, I've got minus 1/2 plus root 3 over 2i. The next one, I've got minus 1. The next one, I've got minus 1/2 minus root 3 over 2i. And then I've got 1/2 minus root 3 over 2i, just in case I need them later on. For the next part of part C, hence or otherwise, determine the position of the other 4 vertices of H, giving your answers as complex numbers in Cartesian form. Now for part C, we are solving the equation beta multiplied by z minus alpha all to the 6 equals 1. And if I compare with the first part of part C, you can see w is equal to beta multiplied by z minus alpha. So if I take the 6th root, I would have beta multiplied by z minus alpha equals the roots we see here. So we have beta multiplied by z minus alpha, that's equal to 1/2 plus root 3 over 2i, negative 1/2 plus root 3 over 2i, negative 1, negative 1/2 subtract root 3 over 2i, 1/2 subtract root 3 over 2i. We know what beta is and we know what alpha is. So we have beta, which is 1 plus I over 64, multiplied by z, subtract alpha, so we subtract 3 subtract 7i, and that's equal to these 6 roots. 1/2 plus root 3 over 2i, negative 1/2 plus root 3 over 2i, negative 1, negative 1/2 subtract root 3 over 2i, 1/2 subtract root 3 over 2i. What we need to do is rearrange for z in each of these equations. So we've got 6 equations which we need to solve. So if we take a look at the first equation, well, I've got 1 plus I over 64 multiplied by z subtract 3 subtract 7i equals 1. So what I need to do with this 1 is multiply it by 64, and then I divide that by 1 plus I, and then I add on to this 3, and I add on to this 7i. And if I solve for z, I get 35 subtract 25i. Now if I take a look at this negative 1, here I would have a minus. And if I solve for z, I get minus 29 plus 39i. Next we have 1/2 plus root 3 over 2i multiplied by 64. So that's going to equal 32 plus 32 times by the square root of 3. And if I work this out, I get my next solution as 19 plus 16 root 3 subtract 9 plus 16 root 3i. Next we have negative 1/2 subtract negative root 3 over 2i multiplied by 64. So here we would have negative 32 subtract 32 root 3 over 1 plus I plus 3 plus 7i. That gives us negative 13 subtract 16 root 3 plus 23 plus 16i. Next, we've got this equation equaling negative a half plus root 3 over 2, so what I need to do is multiply this by 64. So here I would have a plus, and that leaves me with a solution of negative 13 plus 16 root 3 plus 23 subtract 16 root 3i. And then I've got a half subtract root 3 over 2i, multiplying that by 64. We get this result here, and if I work this out, I end up with this solution, 19 subtract 16 root 3 plus negative 9 plus 16 root 3i. Question number 6. We are given that y equals e to the 2x multiplied by hyperbolic sin x. We have to prove by induction that for n belonging to a set of natural numbers, dny over dxn equals e to the 2x multiplied by 3 to the n plus 1 over 2 multiplied by hyperbolic sin x plus 3 to the n subtract 1 over 2 multiplied by hyperbolic cosine x. Now at this point I think it's a good idea to state what we want to show. Ultimately we want to replace the n with a k plus 1. So that leaves us with d to the k plus 1y over dx to the k plus 1 equaling e to the 2x multiplied by 3 to the k plus 1 plus 1 over 2 multiplied by hyperbolic sin x plus 3 to the k plus 1 subtract 1 over 2 multiplied by hyperbolic cosine x. We've replaced the n with a k plus 1. This is what we want to show. Well, using the product rule, we have e to the 2x multiplied by the derivative of hyperbolic sin x, which is hyperbolic cosine x, plus the derivative of e to the 2x, which is 2e to the 2x, multiplied by hyperbolic sin x. And if I factorize out an e to the 2x, we have e to the 2x multiplied by 2 multiplied by hyperbolic sin x plus hyperbolic cosine x. Now, if we take a look at the right hand side and replace the n with 1, we have e to the 2x multiplied by 3 to the 1 plus 1 over 2 multiplied by hyperbolic sin x plus 3 to the 1 subtract 1 over 2 multiplied by hyperbolic cosine x. And if we work all of this out, well, we have the e to the 2x, and here we have 3 plus 1 over 2, which is 2. So we've got 2 times by hyperbolic sin x, and then here we've got 3 to the 1 subtract 1 over 2, so that's just 1, multiplied by hyperbolic cosine x. So the right hand side is e to the 2x multiplied by 2 times hyperbolic sin x plus hyperbolic cosine x. So what we see then is the left hand side is equal to the right hand side, and because of that, the result is true for n equals 1. Our next step is to assume that the result is true for n equals k. So what we will do is we will replace the n with a k. So in other words, dky over dxk equals e to the 2x multiplied by 3 to the k plus 1 over 2 multiplied by hyperbolic sin x plus 3 to the k subtract 1 over 2 multiplied by hyperbolic cosine x. So then, our next step is to try to see what happens when n is equal to k plus 1. And when n is equal to k plus 1, we have dk plus 1y over dx to the k plus 1. Well, using the laws of indices, that's equal to the derivative of dky over dxk with respect to x. Now we know what dky over dxk is. That's what we've worked out here. So we have the derivative with respect to x of e to the 2x multiplied by 3 to the k plus 1 over 2 hyperbolic sin x plus 3 to the k subtract 1 over 2 multiplied by hyperbolic cosine x. So what we need to do at this point is differentiate using the product rule. So we have the derivative of e to the 2x, which is 2e to the 2x, and then we multiply this by 3 to the k plus 1 over 2 hyperbolic sine x plus 3 to the k subtract 1 over 2 hyperbolic cosine x, and then we add on to this e to the 2x multiplied by the derivative of this bracket, which is 3 to the k plus 1 over 2 hyperbolic cosine x plus 3 to the k subtract 1 over 2 hyperbolic sine x. So if I factorize out an e to the 2x, well, what we have is 2 times by this result. So we have 3 to the k plus 1. And then if I also think about what I have in terms of a hyperbolic sine, I've got this term here, 3 to the k subtract 1 over 2. And all of this is being multiplied by hyperbolic sine x. And if I think about the hyperbolic cosines, I've got the 3 to the k subtract 1. And that's because I've got 2 times by the 3 to the k subtract 1 over 2, which is just this. And then I also have the 3 to the k plus 1 over 2. So that's in terms of the hyperbolic cosines. So if I attempt to simplify this, well, I've got the e to the 2x, that's not going anywhere. And if I simplify 3 to the k plus 1 plus 3 to the k subtract 1 over 2, what I have is 3 times by 3 to the k plus 1 over 2 hyperbolic sine x. And if I simplify this, I've got 3 to the k times 3 subtract 1 over 2. And that's being multiplied by hyperbolic cosine x. So what we have here then is e to the 2x, and here, adding the powers, I've got 3 to the k plus 1 over 2 times hyperbolic sine x, and here I've got 3 to the k plus 1 subtract 1 over 2 hyperbolic cosine x. And that is the result which we wanted to show here. And so what we can then say is, because the result is true for n equals k plus 1, we've just shown that by induction, and if we know that the result is true for n equals k, we know it's true for n equals k plus 1, and as it's true for n equals 1, it's true for all natural numbers. Question number 7. John picked 100 berries from a plant. The largest berry picked was approximately 2.8 centimeters long. The shape of this berry is modelled by rotating the curve with the equation 16x squared plus 3y squared subtract y times by the cosine of 5 over 2y equals 6, where x is greater or equal than 0, as we see in figure 2, about the y-axis through 2 pi radians, where the units are centimeters. We're given that the y-intercepts of the curve are negative 1.545 and 1.257 to 4 significant figures. We have to use algebraic integration to determine, according to the model, the volume of this berry. So, to begin with, we've got our equation 16x squared plus 3y squared subtract y times by the cosine of 5y over 2 equals 6. The volume, that's going to be given by pi multiplied by the integral of x squared with respect to y in between minus 1.545 and 1.257. But what I need is x squared, so I can rearrange for x squared using this equation. X squared is the 16th multiplied by 6 plus y times by the cosine of 5y over 2 subtract 3y squared. So what I can do is I can replace the x squared with this result here. And doing so, we've got pi over 16 multiplied by the integral between minus 1.545 and 1.257 of 16 plus y times by the cosine of 5y over 2 subtract 3y squared. Now here, let's consider this integral of y times by the cosine of 5y over 2. We've got two functions being multiplied by each other, so we'd have to use integration by parts. If I let u equal y, u dash then will equal 1. And if I let v dash equal the cosine of 5y over 2, that means v will equal 2/5 times by the sine of 5y over 2. So the integral here is equal to u times by v, so that's 2y over 5 times by the sine of 5y over 2, subtract the integral of v times by u dash, so we subtract the integral of 2/5 times by the sine of 5y over 2 with respect to y. And if I work out the integral, we end up with positive 4 over 25 times by the cosine of 5y over 2. So now that we know that, we can now find out the volume by integrating this result. Well, if we integrate the 6, we end up with 6y, and if I integrate the negative 3y cubed, I end up with negative y cubed, and if I integrate y times by the cosine of 5y over 2, I end up with the result I've just found here in red. And I'm evaluating this between minus 1.545 and 1.257. So let's work all of this out. What we have is pi over 16 multiplied by 6 times by 1.257 subtract 1.257 cubed plus 2/5 times by 1.257 times by the sine of 5 times by 1.257 over 2, and then we add on 4 over 25 multiplied by the cosine of 5 times by 1.257 over 2. As we see here, and then we subtract pi over 16 multiplied by 6 times negative 1.545 subtract negative 1.545 cubed plus 2/5 times by negative 1.545 multiplied by the sine of 5 over 2 times by negative 1.545 plus 4 over 25 times by the cosine of 5 over 2 times by minus 1.545. So if I work this out, we get the value shown here. We get a value of 2.26 centimeters cubed to 3 significant figures. Given that the 100 berries John picked were then squeezed for juice, we have to use our answer to part A to decide whether in reality there is likely to be enough juice to fill a 200 centimeters cubed cup, giving a reason for your answer. Well, we've got 100 berries, so what I need to do first of all is multiply this value by 100. So that gives 225.9 etc. centimeters cubed. So for part B, there is not likely to be enough juice to fill a 200 centimeters cube cup. Although the model predicts the total volume of berries to be 226 centimeters cubed, some of this volume would be pulp and it would not produce that volume of juice. Question number 8. Given that a cubic equation has 3 distinct roots that all lie on the same straight line in the complex plane, for part A we have to describe the possible lines the roots can lie on. So for part A, there's 2 situations. The first situation is the cubic has real coefficients. And if this is the case, well, the roots could all be real, in which case they will lie along the real axis. So here's a diagram to illustrate that. If we've got real roots, the roots will lie along the real axis. The other situation we could have when we've got real coefficients is we could have one real and 2 complex conjugates. In this case, since complex conjugates are reflections of each other in the line y equals 0 or the real axis, we've got a vertical line. And that vertical line has equation x equals a. So what we're saying over here is we've got one of the roots, which is real, that lies on the real axis. One of the roots is complex, which means the other root must also be complex, and these roots are complex conjugates. Because we have a straight line, we join the complex conjugates with the real root to form a vertical line. Now the other situation which we could have is if the cubic has complex coefficients, and in this case we could have any straight line. F of z is equal to 8z cubed plus bz squared plus cz plus d, where b, c and d are real constants, and the roots of f of z are distinct and lie on a straight line in the complex plane. We're given that one of the roots is 3 over 2 plus 3 over 2i, we have to state the other 2 roots of f of z. Well, here we'd have to use the idea we see over here. We've got one real root and 2 complex roots, and what we also have is real coefficients. So for part B, we've got f of z equals 8z cubed plus bz squared plus cz plus d. And we've got this complex plane, and we've got this vertical line. We know one of the roots is z equals 3 over 2 plus 3 over 2i. So the other root is the complex conjugate of this, 3 over 2 subtract 3 over 2i. And the third root then must lie along the real axis. That root is given by 3 over 2, which means the roots are z equals 3 over 2 and 3 over 2 plus minus 3 over 2i. G of z is equal to z cubed plus pz squared plus qz plus 12, where p and q are real constants and has 3 distinct roots. The roots of g of z lie on a different straight line in the complex plane than the roots of f of z, and given that f of z and g of z have one root in common, and one of the roots of g of z is minus 4, for the first part of part C we have to write down the value of the common root. Well, for part C, we've got g of z that's shown here, and here we've got one of the roots as minus 4 that lies along a straight line, and the other root, which is common, is 3 over 2. So the common root is 3 over 2. We now have to determine the value of the other root of g of z. So for the next part, we've got alpha, one of the roots as minus 4. We've got beta, the other root, as 3 over 2. And what we know, if we consider the product of the roots, if the other root is gamma, the product of the roots is equal to minus 12. So we have minus 4 times 3 over 2 times gamma equals minus 12, in which case gamma is equal to 2. So we can add that root over here. For part D, hence solve the equation f of z equals g of z. So for part D, let's consider f of z. We know it's got roots 3 over 2, 3 over 2 plus minus 3 over 2y. If that's the case then f of z, that's equal to z minus 3 over 2 multiplied by z minus, then in brackets 3 over 2 plus 3 over 2i multiplied by z minus, then in brackets 3 over 2 minus 3 over 2i. Let's consider multiplying all this out. So we've got the 2z minus 3. This will still give us a root of 3 over 2 when we set f of z equal to 0, multiplied by 2z minus 3 subtract 3i multiplied by 2z subtract 3 plus 3i. So if we work this out, we get 2z minus 3 multiplied by 2z minus 3 squared plus 9. So we've got 2z minus 3 multiplied by, and if I work all this out, I get 4z squared subtract 12z plus 18. I'm going to leave that alone. If we now consider g of z, that's got roots 3 over 2 minus 4 and 2. That's what we worked out in part C. So we've got g of z equals z subtract 3 over 2 multiplied by z plus 4 multiplied by z minus 2. So if we work this out, well, here we've got the z minus the 3 over 2. And then here z plus 4 multiplied by z minus 2, that's z squared plus 2z minus 8. So in other words, if I set this equal to this, I've got 2z minus 3 multiplied by 4z squared subtract 12z plus 18 equals z minus 3 over 2 multiplied by z squared plus 2z minus 8. So I can factorise out a 2 from here, leaving me with 2 lots of z subtract 3 over 2. And I multiply this by 4z squared subtract 12z plus 18. And that's equal to z subtract 3 over 2 multiplied by z squared plus 2z minus 8. And if I multiply this 2 into this bracket, I've got the z minus 3 over 2 multiplied by 8z squared minus 24z plus 36. And that's equal to z minus 3 over 2 multiplied by z squared plus 2z minus 8. So now if I take everything to the left hand side and factorise out as z minus 3 over 2, I've got the z minus 3 over 2, then in brackets I've got the 8z squared minus 24z plus 36, and then I subtract z squared plus 2z subtract 8, and all this is equal to 0. So if I simplify this big bracket, well, I still have the z minus 3 over 2, and I multiply this by 7z squared minus 26z plus 44, and that's equal to 0. So solving this equation, we end up with z equals 3 over 2, that's our common root, and then we've got z equals 13 plus minus square root 139i all over 7. Question number 9. A patient is treated by administering an antibiotic intravenously at a constant rate for some time. Initially, there is none of the antibiotic in the patient. At time t minutes after the treatment began, the concentration of the antibiotic in the blood of the patient is x milligrams per milliliter. The concentration of the antibiotic in the tissue of the patient is y milligrams per milliliter. The concentration of the antibiotic in the patient is modelled by the differential equations dx over dt equals 0.025y, subtract 0.045x plus 2, dy over dt equals 0.032x, subtract 0.025y. We have to show that for part A, 40,000 d squared y over dt squared plus 2,800 dy over dt plus 13y equals 2,560. So for part A, we've got our differential equations. Now what we want is stuff involving y's only, which means then it makes sense for us to differentiate our second equation to find d squared y over dt squared. And if I do that, well, differentiating 0.032x with respect to t, we end up in 0.032 dx over dt, and differentiating negative 0.025y with respect to t, we end up with negative 0.025 dy over dt. Now at some point I'm going to have to substitute this dx over dt into here, but the problem is the dx over dt involves an x, and we don't want an x. So what we can do with our second equation is rearrange for x. If we have dy over dt equals 0.032x subtract 0.025y, we can rearrange for x. X is equal to 1 over 0.032 multiplied by dy over dt plus 0.025y. And if we work this out by expanding 1 over 0.032, that's 125 over 4. We then multiply that by dy over dt, and 1 over 0.032 multiplied by 0.025y, that's 25 over 32y. So now, d squared y over dt squared, we've got the 0.032 multiplied by dx over dt, and dx over dt is 0.025y, subtract 0.045x plus 2, and then we subtract the 0.025 dy over dt. So, expanding, we've got 0.032 multiplied by 0.025y, which is 1 over 1250y. Then we've got the 0.032 multiplied by the negative 0.045x, which is 9 over 6250x. And we've got the 0.032 multiplied by the 2, which is 8 over 125. And then we of the 0.025 dy over dt, which is 1 over 40 dy over dt. So we've got 1 over 1250y, subtract 9 over 6250, multiplied by x, which is what we worked out over here, which is 125 over 4 dy over dt, plus 25 over 32y, and then we add on 8 over 125, and then we subtract 1 over 40 dy over dt. So, collecting like terms, we've got minus 7 over 100 dy over dt, subtract 13 over 40,000y, plus 8 over 125. That's what d squared y over dt squared is. And if I rearrange, we've got 40,000 d squared y over dt squared, plus 2,800 dy over dt, plus 13y equals 2,560. Part B, determine according to the model a general solution for the concentration of the antibiotic in the patient's tissue at time t minutes after the treatment began. So we need to solve this differential equation to find a general solution. If we find our auxiliary equation, we have 40,000 m squared plus 2,800 m plus 13 equals 0. And if I solve for m, we get minus 0.005 and minus 0.065. We've got real distinct solutions, which means our homogeneous solution is equal to ae to the minus 0.005t plus be to the minus 0.065t. Now, if we find the complementary function, for the particular integral, we've got a constant term, 2,560. So our particular integral will be of the form y equals k. And if I differentiate this once, I get 0, and differentiating again, I get 0. So now we need to substitute these back into our original differential equation, which leaves us with 13k equals 2,560, which means k is equal to 2,560 over 13. Which means our general solution is a sum of the homogeneous solution ae to the minus 0.005t plus be to the minus 0.065t, and then we add on our particular integral. Our particular integral is y equals k, and we know what k is, so we add on to this 2,560 over 13. This is our general solution. For part C, hence determine a particular solution for the concentration of the antibiotic in the tissue at time t minutes after the treatment began. And for this question, we'd have to use our initial conditions. There's no antibiotic in the patient. So for part C, we've got the condition t equals 0 and y equals 0, and if I substitute that back into here, we have ae to the 0 plus be to the 0 plus 2,560 over 13 equals 0, which means a plus b equals minus 2,560 over 13. We also have the other condition. Well, we've got dy over dt. If I differentiate this, I end up with minus 0.005 ae to the minus 0.005t. minus 0.065 b e to the minus 0.065t. And if I use the condition t equals 0, x equals 0, and dy over dt equals 0, setting this equal to 0, we end up with minus 0.005 a e to the 0, subtract 0.065 b e to the z equals 0, which means we've got minus 0.005 a minus 0.065 b equals 0. If I solve this equation with this equation simultaneously, we end up with a equals minus 640 over 3 and b equals 640 over 39. Knowing what a and b are, we can now state our particular solution. Our particular solution is given by minus 640 over 3 e to the minus 0.005t plus 640 over 39 e to the minus 0.065t plus 2560 over 13. To be effective for the patient, the concentration of antibiotic in the tissue must eventually reach a level between 185 mg per milliliter and 200 mg per milliliter. We have to determine whether the rate of administration of the antibiotic is effective for the patient, giving a reason for your answer. Well, because it talks about eventually reaching a certain level, what we need to do for part D is see what happens when t tends towards infinity. When t tends towards infinity, this term tends towards 0, this term tends towards 0, so we are left with y tending towards 2560 over 13. And 2560 over 13 is 196.9, etc. And you'd find that is in between the 185 and the 200. So because this is in between 185 and 200, we can therefore say that the method of administration is effective.